Right, this video is question 3 of the Level 2 2019 Waves exam. Question 3. Mountainous regions make radio communication and signal reception particularly difficult. As a result, transmitters need to be strategically placed and use correct frequency to ensure the signal is received. Transmitters below is set to broadcast throughout the region. Fred lives in a house between two hills. He enjoys listening to old-fashioned FM radio stations. If the radio transmitter uses a frequency of 95 megahertz, show the time period for the waves is 10.5 nanoseconds. Geez, that's diabolical, making year 12 remember what megahertz and nanoseconds stand for. But anyway, 95 megahertz is, so that's the frequency. F equals 95, it's times 10 to the power of 6 hertz, or 95 million, mega meaning million. And 10.5 nanoseconds is 10.5 times 10 to the negative 9. Right, so you're using to define, so we're trying to find, what is trying to find? Time period. Time period on your formula sheet, T is equal to, okay, I'll write it up here. The frequency is equal to 1 over the period. So if you go flip this is F over 1. You can think about that. F divided by 1 is equal to 1 divided by T. You just flip both fractions and you get T over 1 essentially, or divided by 1 is equal to 1 over frequency. This would technically be time divided by 1, but time divided by 1 is just time. So that is going to be equal to 1 divided by 95 times 10 to the 6, and that equals 1.05 times 10 to the negative 8. That equals 1.05 times 10 to the negative 8. 0.05. Serves me for talking, which is essentially, the period is equal to 10.5, and that is seconds, units, nanoseconds. There we go, NS. Right, that's quite a tricky question for level 2, just because it requires a lot of sort of weird previous knowledge. Anyway, describe the phenomenon that allows the transmission to be received at Fred's home despite the transmission tower being out of sight of his house. Include a diagram in your discussion to explain whether or not longer wavelengths would make reception of signals better for his house shown. So it's diffraction. So diffraction is the spreading out of waves as they propagate. I suppose that's probably the way to explain it. And larger waves diffract more when like hitting a barrier. But that's kind of a weird way to explain it. It's just, I'll try and draw a picture and maybe explain it that way. So here we have longer wavelengths. So here, imagine we've got wavefronts go like this, quite large, sort of like that. And then what ends up happening is they end up diffracting around the bend, like so. And then, so if this is, and we'll just have this, I'll try and keep this, this is lambda, this is lambda, just to show this is lambda. They're all meant to be the same wavelength. The same, damn it, you can't even see that, whoops. All the wavelengths are meant to be the same. So here you can see the waves propagate out, I suppose. And this point here, as they bend down towards the house, that's called diffraction. If, however, do I have a different color pen? No, I don't. If you have a really, really short wavelength that's emitted from this, what ends up happening is you just get a whole lot of lines like this. I'll try and draw it. This is so messy. I should really use my ruler. Yeah, I'll try and draw it. They won't even be curved actually. They'll just draw straight lines. Like that there. And what ends up happening is you get a little bit of diffraction. A little bit. But not much. Like only the smallest amount. I'll just keep on going, keep it going. it's a bit tedious, but you sort of get the picture. You get a little bit of diffraction, like the smallest amount, but not really. So you get the smallest amount of diffraction here, but not really. So I'll pause it, write an answer, and then just explain it. Right, so I said the phenomena is diffraction when waves spread out when hitting a barrier similar to the wavelength. Similar to the wavelength is probably sort of a way to explain it. From the diagram, larger wavelengths diffract more, thus would give better reception. It's a really simplified explanation of it. If you really want to look up, it's called Huygens principle, Huygens. That's HUY. It's Huygens principle where every wave can be modelled as a spherical circle which spreads out. If the wavelengths are really close together, you end up with high, what do you call it, definition? I'm trying to think of what's resolution, I suppose, would you call it. So larger wavelengths have really low resolution, shorter wavelengths have really high resolution, which means they're all really close together. You do get diffraction of light on any edge. It's just your human eye can't really see it because the resolution is so sharp that it doesn't really make a difference. Anyway, I'll move on because I'm just rambling. What do we got? Second transmitter broadcasting on the same frequency is built next to the opposite mountain. There and there, pulse is sent from each tower. Sweet. Draw the resulting superposition after 3 seconds. Sweet. So now what I'm going to do is I'm going to just mark, this is, I'm going to keep everything on the same square. So this one here is going 1 grid per second. So we're going to go, I'll just do the leading edge. 1, 2, 3. So go down this one here. So I need to go, now I'm going to draw this is like the way to do it. You draw them both over top of each other with dotted lines. So I know this is the shape, he's moved forward 3 squares. So he would essentially, I need to go how many up? 4 squares. So up 4 squares, across 3 squares, down 3 squares, and he would have had continued out like that. So that is his new position. And then this one here is moved forward 3 seconds, so he or she. 1, 2, 3. So then we come down to here, and this one is up 3 seconds. So we're going to go up here, and it's 2 across, isn't it? It's 2 across. Right. So the new pattern will be this. I'll grab my ruler. I'm going to trace out to here. This has only just got so this one here, this portion here is just this portion here. So I'm just going to draw straight up, and then I'm going to go across, and then this 3 squares here is overlapping into here. So they're going to add together. So I had 4 squares plus the 3 squares from that one. So we're going to go 4 squares up 3 squares. And then we're going to have something that looks like this, going up. And then we're going to have it going, I'll just fill in the gaps. And then we're going to go back the 2 squares from here. That was a bit wonky, wasn't it? And there we go, and then I'll just push that across. A little bit wonky, but not too bad. And then we'll just, maybe, do we shade this in? Nah, you can see it sort of pretty clearly. So that's how you do it. You just use dotted lines to draw the squares, and then the points where the squares would overlap, they add together. If the squares were on the other side, they'd subtract off each other. Right, there we go. I hope that sort of makes sense, the mechanical way of doing it. Right, last question. When a second transmitter transmitting the same frequency is added, explain with reference to wave interference why some locations of the valley may receive boosted signal while others may not. So this is going to be talking about constructive and destructive interference. Constructive will where the antinodes of the waves will line up, and destructive will where the nodes where the antinode and a node line up to create no wave. So I'll pause it, write out a kind of neat answer, and then I'll discuss it. Right, so I've said locations where you would receive a boosted signal are, there should be are places where the waves from each transmitter arrive in phase and constructively interfere. I should have chucked in, this is where two antinodes combine to create a larger amplitude, but I had to write that down the bottom because I just didn't think of it at the time. Increasing the wave amplitude bracket signal. Amplitude signal, same thing. Places where the waves from each transmitter arrive out of phase. Destructively interfere. This is where a node and an antinode combine to create no wave. I just thought about that, and node and antinode, no meaning no wave, or like the this isn't where a node and an antinode combine to create no wave. No, this is where I need to cross that out actually. This is when a positive antinode and a negative antinode combine to create no wave. This should be positive. There you go. To create no wave. At this point, the amplitude will be smaller, 0, so weaker signal. I've chucked down the bottom when path difference between waves is a whole wave, two positive antinodes add, creating constructive interference. I'm not sure how far to go in with level 2. It's always kind of a bit confusing with these questions because you can really go into detail and you can go into sort of level 3 detail. You have essentially, if I draw down the bottom, you have two versions. You've got, I'll just try and draw this now. Well, there we go. And then, so this is going to be constructive interference. So this would be constructive interference, and this would add to create a wave a lot bigger. Same frequency. So this is constructive interference. Destructive interference is when we have same waves, but we have one of the waves out of phase. If I can try and get it out of phase, there we go. So this peak will add with this trough to create no wave whatsoever. So the amplitude will be 0. So this is constructive, destructive, and this is destructive, destructive. So probably not the best answer I could have ever given, but I hope I've explained how this whole thing works. So here you wouldn't actually get any signal whatsoever. Here you would. In reality, if you do this in the real world, you just get points where the signal becomes weaker and larger because you get all this bouncing off the ground and stuff like that.